Sen qaydan bilasan?
Balki bu ko'zlar unsiz bir qo'shiqni kuylayotgandir. Kuylayotgandir.
Kuylayotgandir.
Kuylayotgandir.
Sen qaydan bilasan?
Balki keng olam shu mo'jaz qalbimga bo'ylayotgandir.
Sen qaydan bilasan?
Balki meni ham kimdir qaydadir jim o'ylayotgandir. O'ylayotgandir.
O'ylayotgandir.
All right, hello, grade 11s. How is everybody doing? Okay, let's get some stuff set up here. Okay, mic is on, and I think we're live. Wonderful. How's everyone doing? Okay. Cool. Hello, Arman. How are you? Today we're going to be looking at just essentially the circuit practice we posted back on the Tuesday. Good, thanks for asking. Right, so we're just going to answer some of the questions from there. Yeah, let's go from there. Let's just quickly first check out our question doc. I see we have a couple questions already. So why does a circuit have to be closed in order for energy to pass through? It's not that it has to be closed. 99% of the times things we work with in the real world, circuits need to be closed because that's the easiest way to go from a high potential to a low potential. And the way circuits are set up, even a battery, the electrons come from the high potential side and go to the low potential side. So, well, literally the high potential and low let's draw this. Okay, let's draw it. Oh, by the way, today I'm not going to go through every single question. I'll take some questions here and there, obviously, but the main thing we're going to go through is this one because I think this one was quite a bit more annoying than some of the other ones, especially number 2 over here. We're definitely going to go through that one. If you have questions about this other one, I'm going to post a solution set to this one. You can just check your numbers and see how you did. All the ones here are combined circuits, but you know, once you've done one, you've kind of seen them all. Sure. Okay, so let me just quickly jump into PowerPoint here. I'm going to answer the questions that were posted on the doc. So the question was, why do circuits need to be closed for electrons to pass through, or whatever along those lines? So why do circuits need to be closed? Why do circuits need to be closed? So I mentioned a couple things before. Well, 99% of the times, so let's do the 99% of times, the easiest way for electrons to go from a high potential, so let's say this is the positive side to the negative side, the easiest way for, actually, well, we know the electrons actually go the other way around. By putting conducting wire to connect the positive and the negative terminals, we have essentially, let me get a different pen here. We have energetic electrons here, energetic, G-E-T-I-C, electrons, and they need a way to go to a place with low potential. The same way, let's say, let's use the ball analogy. Here, the ball has an easy time going down to a low potential because, well, the hill is open. What if we put a barrier, though, right? What if we made little walls around the ball here? If we put a barrier here, well, now something is obstructing it from going down. You want to think of the wire as being a path for the electrons to go from a high potential area, high pot, to low pot. Now, the other way we could do that, and I mentioned it kind of shortly last time, was to ground something. Same deal here. Let's say, you know, you're playing outside with your, I don't know, a flagpole. Your favorite flagpole to play, I don't know. You're having a blast. holding your nice long flagpole. Yes, excellent. And above you are these dangerous power lines. Now, we mentioned that, ground is another way for electrons to go to a lower potential. As a whole, the Earth is so big, it can accept almost an infinite amount of electrons. So its potential is always practically zero, so to speak. Another way, so using a battery or power source like your outlet gives an easy way for the electrons to go back to the source in a low potential way. Here, we don't have to send the electrons back to the source. It just has a shortcut to a low potential. Hopefully, if the flag is on the ground, a metal flag, whatever. Actually, even a wooden stick, because the potential in these wires is so high, the electrons can travel down the pipe and get to the Earth, where it's from a high potential here to a low potential, which is the Earth. And if the flag is in contact with the Earth, it's okay. If you're holding the flag above the ground, well, your body will be the part that closes the circuit to take the electrons from a high potential area to the ground. That's why ground is also considered, another escape point, or a point where electrons can leave. Okay, so we got a couple of things ahead of us. We're going to just go through each circuit. I think we'll leave this one for last. It's probably the most challenging one. Yeah, okay, let's jump into it. Oh, there was another question. Oh, sorry. Let's have a look. Where were we? Here and here. How can you tell if you should simplify How can you tell if you should simplify a combination circuit to series or parallel? You have to look at the overall structure. Sorry, sometimes I have a hard time reading. Where are we? No, not here. Let's look at the first example. This one over here, well, the first thing I may want to do is just to redraw everything. Okay. This is our positive terminal. This is our negative terminal. For conventional current, we go from here to here. And if I wanted to redraw everything, let's just draw it like as a path. So we're starting at the positive terminal. The first resistor we encounter is that 4 ohm resistor. The 4 ohm resistor. Next, we get a choice. We reach a junction where the electrons have choices now. We can either go through the top path or to the bottom path. In the bottom path, let's have a look. In the bottom path, I'm going to say this is the bottom path. Then we have the 2 ohm resistor. Then we go into the 2 ohm resistor. Then also has another junction here, but where the electrons split up, and they go through a 12 ohm resistor and a 6 ohm resistor. I'm just going to do it like that. And then they recombine at the opposite junction, and there's another junction over here. And on the top one, there's only that 3 ohm resistor. 3 ohms. And everything meets up back at this junction again, and then passes through a 1 ohm resistor. Okay, let's have a look. Once we redraw it like this, this is one way you can redraw it. There's actually multiple ways you can do it. If you wanted to, then if you want to be really professional, I guess, you would just circle it back to where we came from. Great. Now look at these electrons. There's only one path, so to speak. Sure, it splits up at many points and then it comes back, but this 4 and this 1, all electrons are forced to pass through these two specific ones over here. Whereas if we look at, actually, I would do all of our circuits today as series circuits, because their overall structure is series. Let me show an example when their overall structure would not be series. An overall structure that is not. The reason why the overall structure is series is because there are some resistors in all of them. In this resistor, because of the 1 and the 4, it takes all the electrons. Definitely series. Here, this resistor 1 takes all the electrons before you reach a junction. So I guess here, this is the way you want to think about it. If your electrons pass through a junction before a resistor, or if there's a resistor that all the electrons get, it's series. If there's always junctions before you reach a resistor or come back to your power source, then it's going to be parallel. Let me show you an example. So an overall structure of a combined circuit that is parallel, let's do this. Let's say we reach a junction first, so boom, first resistor, second resistor, this one, 1, 2, and let's say 3 even, whatever. So 3 resistors on that one, and this one, let's say there's only 1 resistor. Okay, since our electrons split up before they get to any resistor, this would be overall parallel. This can be imagined as combining these two, these ones, and these ones to just look at it as a circuit that looks something. Oh, I did it the wrong way around. Okay, I'll fix that. As a circuit that looks like this, where we have, let's label everything. Let's call this, let's get a different color actually. Let's go green here. Let's call this 1, 2, 3, 4, 5, and 6. So 1 and 2 are combined into 1 here. Then we'll combine 3, 4, 5, and then just the 6 on the end. So in the end, it just results in a well, it's not a single, a parallel circuit where we were able to combine everything else. But what made this one different than all the other ones that we're going to do today is that we had junctions before we had resistors, or none of these resistors that I drew here will get all the electrons. They're only going to get some portion of the electrons. So if the current splits up and no one resistor gets all the current, it's going to reduce to a parallel circuit. When we have circuits where a resistor receives all the electrons, this R1 here, all the electrons are forced to pass through it, we want to consider that as series. So in fact, we're going to eventually combine all of these electrons into one. After you combine 1, 2, and 3, yeah, you get a series, but then good question. So our man's saying, what if you combine all these 3 to get one single resistor? Yeah, then you can combine everything to a single resistor, and that's what RT does. When you calculate RT, that's combining all our resistors into one. And now when it fits one thing, it's not really series or parallel, because we say 2 light bulbs are in series with each other. We talk about series as how loads are arranged with each other. That's a good question. So yes, we reduce everything down to 1 resistor, but the overall shape of a series versus parallel is determined by how much current it gets. Why did I use this description earlier? An easy description is, if I were to remove any one light bulb, can I turn off all the light bulbs in the circuit? So if I remove this 4 ohm resistor, everything else goes dead because I've broken the circuit. Here I can do the same. If I remove this R1, everything in the circuit goes dark. If I remove this 270 ohm resistor, every light bulb goes dark. However, in this one, I can remove any one light bulb and others will still be able to light up. If I remove number 1, sure, number 2 goes dark, but 3, 4, 5, and 6 all are lit up because they have other paths. So maybe that's another way you want to look at it. So either through current, or are you able to move any one light bulb and turn off the whole circuit? Ask yourself that. Okay, so let's get into it. Let's actually calculate some numbers. So actually first let me just type some stuff in here. So we're going to do voltage, we'll do current, and we'll do resistance. 1, 2, 3, 4, 5, 6. I need another row, column. Insert columns right. Okay, and then total. Okay. Hopefully everyone's okay with that. In fact, let's actually copy this over to a different page. This and this. Control C. Just because this one got a little bit messier than I wanted. Alright. Good questions, by the way. Did I answer that last one? Where are we at? Okay. Yeah, I think I'm good. Okay. Let's get into it. So, maybe we'll start off by just saying, what do we know? What do we know? Well, we're told each individual resistor. We didn't have numbers for them yet. You can number them the way you like. I like to go starting from top, work my way bottom. So I'll call this resistor number 1. This will be resistor number 2, 3, 4, 5, 6, and it doesn't matter as long as you're consistent with whatever you use. If it's not labeled in the beginning. So we have them all. So what do I know? I know all my resistances. I'm going to put them in. So resistor number 1 had 1 ohm resistor. Resistance number 2 was a 3 ohm resistor. Resistance number 3 was 6. 4 was 12. 5 was 2. And 6 was 4. Wonderful. I cannot add them all up because this is not a series circuit. I will have to use both parallel and series rules to combine my numbers. Voltages. I don't know the individual voltages. However, I do know the total voltage. The total voltage from our power source. Oh, there's a little resistor here. We're going to ignore that because it's not labeled. In case anyone's wondering. Sorry for that confusion. Our total voltage for the whole circuit, the amount of energy each electron gets, is 8 volts in the beginning. Okay. So, like we said before, normally the way we go about it is first finding our total resistance, and then we'll go into seeing what we can do. Okay, so first things first, let me actually go home. Let me grab this. Control C, Control V. I'm going to take this, and I'm going to start combining resistors wherever I can. So, you know what? Let's do that on a separate page. I'm going to Control X that. I'm going to Control M this. Okay. Control V. Okay. Let's start combining resistors. Boom. Okay. So I go to my pens and I go over here. Okay, and I look at what can I combine? Well, if I redraw the circuit, there's a junction here, there's a junction here, there's a junction here, there's a junction there, and there's a junction there. I'm talking about junctions as every time electrons split up or combine from different paths. Okay. Let's have a look. So, I know that eventually, or these two are parallel with each other. I will be able to combine them with together. So let's combine these two resistors together. What did I number them? 3 and 4. So if we do 3 plus 4, we have to use our parallel rules. 1 over R P is equal to 1 over R4 plus 1 over R3. We do some calculation bits. 1 over RP is equal to 1 over 6 plus 1 over 12. Actually, these are nice numbers. If you add them up, that becomes 2 over 12. So we get 1 over RP equals 3 over 12, because this is 2 over 12 plus 1 over 12, 3 over 12. Now, remember, when we're working with parallel, we got to flip that fraction to get that resistance total. So RP parallel, this combined 3, 4 resistor, so I'll just say 3, 4, 3, 4, 3 plus 4, is equal to 3 divided by 12, which is 4 ohms. Okay, we've made some headwork here. Let me draw that out. So, this one over here, what I'm calling R34, is equal to 4 ohms. Wonderful. Now, I've combined those two. What's next can I combine? I can't combine any of this stuff yet, because this 3 ohm resistor is parallel with all of this. So maybe the next step is, okay, I combined 3 and 4. 3 and 4 were series with 2. Because the electrons that passed through the 6 ohm resistor and through the 12 ohm resistor eventually combined and went back into the 2. So, a different color. I wonder if I have enough colors for all this. We'll give it a shot. Let's do green. So I'm going to combine resistor 5 with 3 and 4. Okay, so all of this now, since this is a 4 ohm resistor when we combine 6 and 12, the resistor 3,4 is in series with resistor 5, so resistor 345 is equal to resistor 34 plus resistor I lost it 5. So we're doing 4 ohms plus 2 ohms because they are in series with each other. So we get 6 ohms total for the green one. Resistor 345 is equal to 6. Yay. Okay, maybe I might want to redraw the diagram, take a look at what I've done so far. Okay, so I'm going to redraw our diagram. Actually, no, I'm just going to copy paste. Wonderful. Where is my home? Let's go home. Let's grab this. Control CV. Okay, so what have we done so far? We've combined all of this chunk. I'm going to highlight it. That's one resistor now. And all of that resistance is equal to 6 ohms. All right. Now, this resistor of 6 ohms, that looks ugly. Let's fix it. Let's just keep it simple. All of this is equal to 6 ohms. 6 ohms. Okay. Now, the 3 ohm and the 6 ohm are parallel with each other. The combined 3, 4, 5. So we have to do parallel rules once again. We do parallel rules once again. So resistance 1 over Rp for, let's do a different color. And by the way, this is all just to calculate what is the total resistance of the whole circuit in order for us to figure out things like current and voltages later down the road. So we're going to combine 3, 4, 5 with this resistor 2. I think I called that 2. Resistor 2. Let's go for it. They're parallel with each other, so we have to do with the 1 over Rp business is equal to 1 over R345 plus 1 over R2. Okay, 1 over R345 was 1 over 6 plus 1 over 3. And now these are nice numbers also. 1 over 6 plus 1 over 3 becomes 3 over 6, which is equal to 1/2. And then the last bit, like I said, since we do parallel rules, we need to bring that Rp up. So we take the reciprocal once we've done the addition. We cannot do the reciprocal before that because we don't know what that number is. So the resistance for 2, 3, 4, 5 is equal to 2. So we have just combined all of this and we figured out all of the brown area is 2 ohms once we've added all of these resistances. Whew. Anyone sweating yet? Okay. The hard work is done. Because what have we reduced it to? If we copy down, let's paste that same, let's paste it in again. What have we done? We've finally combined everything so it is a series circuit. Let's actually do it. Let's go to a different page. Let's go to a different page. Next one. What have we done? Goodbye. Goodbye. Let's actually make this big. And I'm going to write actually all my numbers in here. Or most of them. Rather. Okay. Okay. Let's see if I can remember the colors here. Okay, so I used cyan for this one. So, step by step, what did we do? We combined similar kind of resistors if they were parallel or series in order. So the first thing we could do is combine the 6 and the 12, and we got, I believe we got 4 ohms. Then we combined these two together, and we got 6 ohms for all of these. 6 ohms. And then we combined it with the 3 ohm resistor in brown, and we got 2 ohms. So wait a second. That's like saying we had an 8 volt power source, then our 4 ohm resistor, 4 ohms, then a 2 ohm resistor. This 2 ohm resistor was everything we calculated in the previous slide. Then a 1 ohm resistor, and then 8 volts again. Isn't this beautiful? Getting to this point, it's very satisfying. So try it out on your own if you haven't got this already. If you got this, great. Because now we finally created a series circuit. It's no longer mixed. It's a pure series circuit because everything goes to the 4 ohm, to the 2 ohm. Well, the 2 ohm is actually pretty complicated, like we've seen. And then it goes into the 1 ohm and then back. So what is the resistance total now? That was equal to resistor 1 plus resistor 2 to 5, and then plus resistor 6. So resistor 1 was just 1. Resistor 2 to 5, we calculated all of that. Resistor 2 to 5 was 2 ohms. And then plus resistor 6 was 4. Oh, isn't that nice? We get 8 ohms. Let's break that back in here. So what did we figure it out? The total resistance of this whole circuit was 8 ohms. Yay. We use some formulas here. V is equal to IR. I is equal to V over R. R is equal to V over I. Let me just double check, make sure I did okay. V over I. I is equal to V over R is equal to, yeah, looks okay. Now, so, current is equal to voltage divided by resistance, so we get a 1. Nice. We get a 1. Anything else we can do? Wait a second, now we can analyze our circuit. In this diagram here, how much of the current did this 4 ohm resistor get? It got everything, because all the electrons were passing through 4. Then they split up, but in the different branches, if we added up all the currents for resistor 2, 3, 4, and 5, if we added all those currents up, well, that's all the current, because everything came from that power source. Then all of them combine again and hit the 1. So, resistor 4, resistor 1 get all the current. Okay, so resistor 4 and resistor 1 get all the current, so I can put those numbers in. They get also 1 ohm here, they also get 1 ohm here. That takes us to the next step. We can calculate their voltages. As soon as we get 2 numbers in any column, we can get the next step. Z says 1 plus 2 plus 4 is 7. I don't like your math, Z. You're right. Oh, no. Okay. I wanted it to be 8. I wanted it to be 8 so badly. Just because then it makes my numbers easier. Thank you. Yeah. So this is 8. Minor correction. I gotta fix this. See you later. Analysis still works, but I can't add, apparently. Thank you, Z. Thank you, Miss Varag. Okay, so I got a calculation step. Let me calculate what the actual resistance is. It's going to be 8 volts divided by... No. Yeah, the current will be 8 volts divided by 7 ohms. So let me get that new number instead. It's going to be like 1.2 or something. 8 divided by 7. As a no, it's 1.14. Okay, I can fix that. I can fix it. 1.14, 0.14. The analysis still stays the same. All the electrons have to pass through the 4 ohm. They split up inside the 2 ohm, but all of them combined is still all of it. Then all of the current passes through the 1 ohm. Then we can calculate their voltages. So how much energy is taken away by the 4 ohm resistor and by the 1 ohm resistor? Let's calculate that. Let's break it out. So voltage is equal to my resistance times my current. So that's 1.14. And then, so I just did 1 times 1.14. 12 times 1.14, I cannot do in my head. 1.14 times 12 equals, I'm getting 13.68. Huh. Okay. Now, let's analyze. So, this resistor over here, resistor number 6, took, what is it? Resistor number 6? What the heck did I do? I put it in the wrong place. Sorry. This was resistor number 1. This is resistor number 6. I gotta copy this over. Pens. Resistor 1's the right place. I just saw the number 4 here, and I put it in the wrong spot. Okay. So over here, we had a resistance. Sorry, the voltage was 1.14. 1.14. Now 4 times 1.14 is 6, 5, 4, 5, 6. Okay, good. Okay, so I know of my 8 volts, 4.56 is taken away here. 4.56 volts, and 1.14 volts is taken away here. That means for the rest of the circuit, we have remaining how much voltage. So the rest of the circuit is able to take away 8 minus 4.4. You know what? Let's write it out. Let's do another slide. So now we're going to do voltage this time. Pens. 4.4. Sorry, 4.5. 4.56. This is 1.14. So how much voltage is remaining for the rest of the circuit? If these two take if both of these take 1.14 and 4.56, remember this is in series with all of this combined circuit. Another way to think about it is this 2 ohm resistor gets the remainder of the voltage that's left after the 1 and the 4 take it. Well, obviously not in that order, but we know what they take. So we do, to find the voltage of your, this is from 2 to 5. The voltage 2 to 5 is equal to the total voltage minus the voltage of number 1 minus the voltage of number 6, because this was the overall series circuit. So then voltage 2 to 5 is equal to, we have 8 minus 1.14 minus 4.56. That's the same as saying 8 minus 5 times 1.14. I'm getting 2.3. So the rest of the circuit gets, V 2 to 5 gets 2.3 volts. Wonderful. How does this help us? Let's have a look. Every electron that passes through this junction has to split up and go through the 3 ohm resistor and the rest of them. So when we deal with resistor 2 and resistor 3 to 5, we know that every electron passing through resistor, divide by, didn't you divide 2.3 by 4? I didn't. Did I make a mistake? 8 minus 1.14, maybe I made a mistake here, minus 4.56. I'm getting 2.3. So the 2.3 is how much voltage is there for this section of the circuit. So we don't divide by 4. Even though there are 4 resistors, we don't know how much each gets. In fact, we see that the resistor 2 is parallel with resistor 3, resistor 4, and then resistor 5 is down here. So, since everything coming in has 2.3 volts, everything over here is going to get 2.3 volts. Everything over here is also going to get 2.3 volts. Okay, so resistor 2 also has 2.3 volts. Resistor 2 pens has 2.3 volts. Now that we have a number here, we need to calculate how much current passes through there. Let's get that. So the current is voltage divided by resistance. So 2.3 divided by 3, and I'm getting a voltage of 0.77 amps. Now, if we had to analyze now, remember, how much current is coming out of here? 1.14 amps. This 1.14 amps is going to be split up into 2 locations. If this one has 0.77 amps, we can calculate what is the leftover for resistor 5. So resistor 5 is going to be the 1.14. So the current at 5 is equal to 1.14 minus the total minus the current going through resistor 2, which is 1.14 minus 0.77, and we get the current for number 5. The current for number 5 is 1.14 minus 0.77. I'm getting 0.37. 0.37. Okay, so from there we can calculate the voltage. 2 times V equals IR. We get 2 times this is equal to, what is it, 0.74. Yes. Whew. Are we done yet? Okay. Now, we know that this took 0.74 volts. We also know that the remainder for all of this was, what was the voltage? 2.3. 2.3. That means each of these resistors are going to get the same voltage. They're both going to get a voltage of whatever is the remainder of this. 2.3, the voltage of 3 and 4 is equal to the total or the voltage of number 2 minus the voltage of number 5, which is equal to voltage 2 was 0.74. Did I do the other way around? No. Voltage 2 is here. which was voltage 2 was 2.3, 2.3 minus 0.74. I'm getting 0.3 minus 0.74. Both the 6 ohm and the 12 ohm resistor, 6 and 12, get, what is this as a decimal? 1.56 volts and 1.56 volts. Almost done. Let's just calculate their currents. Let's see what happens. The current is equal to voltage divided by resistance. So 1.56 divided by 6 equals, I'm getting 0.26 here. And on the other one, we're going to get, what is it? 1.56 divided by 12 this time. I'm getting 0.13. Whew. Okay, I think we're done. And the quick check step here is, since we got their individual currents here, the current here was 0.26, the current here was 0.13. When we add these two, that should be equal to the current at number 5. So we add these two, 0.26 plus 0.13, that's 0.39, close enough to 0.37. I think because of the rounding from place to place, they should have probably been 0.38 for both of them, but it's close enough. Okay, what a wild ride. Alrighty. Sure. For this one over here, let's go for it. In this one, I'm only going to do, shoot. I'll post the full solutions at some point, because I'm looking at the time right now. We won't be able to finish. Let's calculate the total resistance, and I'll leave it there. I'll post the rest of the solutions online. Try it for yourself. Yeah. Right. I don't know if I'm happy with that. Maybe I'll post a different video. I don't know. But I'll definitely post the answers. Okay, so let's calculate the total resistance on this thing over here. Okay, we're going to go through it a lot quicker this time because we kind of know the rules. This is going to be dealt with as parallel. Once we deal with those two as parallel, then we're going to get these three as a series, and then these ones are going to be, let's do a different color, red. These four are going to be in series with each other because this 5 is in, oh, did I say series? I meant parallel. This 5 ohm, no, the resistor number 4, parallel. This resistor number 5 is parallel to all of these. The electrons passing through 5 cannot pass through these ones over here. And then we have another set to go through. Let's do it in green, I suppose. Then all of this, 5 to 4, are in series with resistor 7. And then, more to go. Let's do it in brown. All of that, resistor 6, is in parallel with all of this on this side over here. And then at the very, very, very end, let's do it in orange. Resistor 1 is in series with resistor 6 to 2 to 6. What a ride here. Okay. Resistor. What is happening? Resistor 2 to 6. Okay. If this looks really messy, okay, fine. Maybe we'll do it on a separate sheet of paper. Separate page. Slide. Whatever. Control C. Control. Nope. Control M. Control V. Delete. Delete. Let's go through it step by step. Okay. In red. Let's combine these two. Okay. To combine these two, they're parallel with each other. So the red one, let's start off here, is 1 over R2. R2 is 2 ohms. R3 is 3 ohms. Wonderful. 2 plus 1 over 3 is equal to 5 over 6. So then the resistance, well, 1 over R23 is equal to that. So then R23 is equal to 6 over 5. Yay. Let me just double check my numbers. R3 was 3, R2 was 2. Cool. Now, we can combine that with R4. Let's do that in pink. And let's put it off into the corner here. R2 to 4 is equal to R4 plus R23, which was R4 was the 4 ohm resist. No. R4 was 8. 8 plus what we just calculated, 6 over 5. Let's put everything into decimal. This is 6 over 5 is 1.2. So this is going to be 9.2. So all of the pink area is a 9.2 ohm resistor. Way to go. I am proud of myself. Then we'll do everything over here in cyan. Okay, I'm happy I'm actually keeping things relatively neat here. I'm missing a number. This is 2 to 4. Resistance from 2 to 5, well, it's parallel. This part is parallel with all this. So we have to do 1 over R5 plus 1 over R2 to 5, 2 to 4. This one over here. So, well, now I need to consult my calculator because I do not know how to do this without one. 1 over R5 was 5 ohms, very convenient, plus 1 over 9.2. And I'm going to consult my calculator. R2 to 5 is equal to, so I'm going to do 1 divided by 5 equals plus 1 divided by 9.2 equals, and now to take that number and flip it, because to find the resistance of parallel, we have to take the reciprocal. So what do we get? The reciprocal of that is 230 divided by 71 equals, as a decimal, I'm getting about 3.24 ohms. Okay, so that's all of the blue one. Let's combine that with R7, which is easier because it's in series with everything there. Let's do that in green, orange. Orange is good. So all of this from 2 to, well, not 2 to 7, excluding 6. How do I do that? That's annoying. R2 to 5 comma 7 is equal to R2 to 5, which we just calculated, plus R7. So 3.24 plus resistance number 7 is 1. Very convenient. So the total resistance of all the orange is 4.24. Yay. Okay, now we will combine that with the parallel resistor of R6. Are we running out of colors yet? Purple. The old purple. In purple, we can now calculate the resistance. Let's do that in the corner. Resistance from 2 to 7, which is equal to this wonky guy, 2 to 5 comma 7 plus resistor 6. So now we have the full set. Oh man, this is a little wonky. Normally I don't do it like this. Normally, unless you had to show your step-by-step process, I would just put it in a table. But I feel like, you know, going through a step-by-step on stream, it might be helpful. I don't know. You tell me. 4.24 plus resistor number 6, which was, okay. I thought I made a mistake. Oh man, I'll be so mad at myself. 7.24. Maybe I did still make a mistake. Who knows? 7.24 ohms. And voila, we are almost done. Do you have colors? Are we out of colors? We did pink already, light blue, dark blue, and in dark blue, everything. We finally made it a series circuit. All of the blue, if you combine it into one resistor, R1 to 7 is equal to R1 plus R2 to 7, which is equal to that. The first resistor was 4 ohms plus the rest of this, 7.24 ohms is equal to 11.24 ohms. And this is RT because it's the total resistance. Is everyone pooped yet? Is everyone pooped? Let me check out the chat. Looking okay. Let's finish off with the last one. Alrighty. Let's go for it. Okay. Any questions so far? If you have any questions, please let me know. More than happy to help. This one we can solve it completely, but I'm gonna have to do a little bit of running here. Let's label. Actually, no, it's already labeled. 1, 2, 3, 4, 5, and total. Okay. So let us make a table. Insert table. So we have 1, 2, 3, 4, 5. So I need seven columns and 4 rows. Table. Okay. Oh. 7 column, 4 rows. Yes. Okay. So we have good old voltage, current, resistance. 1, 2, 3, 4, 5, and total. Wonderful. First things first, let's put everything we know. Let us just put in everything we know. Okay. Let's actually make this thing as big as possible, easier to see maybe. I'm blocking off something now. Wonderful. There we go. Okay. Whoa. What do we know? We know our total voltage is 18 volts. We can calculate our total resistance. We'll do that in a second. Resistor number 1, 220. Resistor number 2, 130. Resistor number 3, 470. Resistor number 4, 100. Resistor number 5, 270. Let's just not add them all up. We have to combine things appropriately. We have two junctions. Junction over here, junction over here. Meaning, these two are in series with each other. What is happening? What? Oh, okay. That was terrible. We have two junctions. That means these two are in parallel, in series with each other. Every electron passing through, I should draw it the other way around. Every electron passing through resistor 1 is forced to also pass through resistor 2. Let's combine them together. R12 is equal to, well, we can add them. Very nice. So that is 350. 350. Resistance of 1 to 3 is the parallel of this 350 with the 470. So those are parallel. Let's smush them together. So we have to do 1 over 350 plus 1 over 470, all that to the -1, meaning to take the reciprocal. So just going to put that in my calculator, see what you get. So fraction button 1 over 350 plus fraction button 1 over 470 equals, flip that fraction to the power of -1 equals, as a decimal, I'm getting pretty much 200 ohms. And you know what? Just to keep things nice and simple, I'm going to keep 200 ohms. It's 200.6. I want to keep the numbers nice. So what we just calculated, let's do that in a different color. So this one over here is all three, and all three combined to make 200 ohms. Very convenient for us. So now this is a series circuit, so I'm just going to add everything in a different color. So everything. Let's do, we already did red. Let's do purple. All the resistors, RT, was equal to R1 to 3 plus R4 plus R5. It's a series circuit, so we're going to use series circuit rules. So 200 plus 100 plus 270. Very good. So 570. All right, and now we got our answer. So the total resistance of our circuit here, the total resistance, I figured out, is 570 ohms. Let's choose a different color that contrasts better. Red was fine. We got 570 total resistance. Now, current is equal to voltage divided by resistance. So that is 18 divided by 570. I'm getting 0.032. Okay, I gotta keep a couple of decimal places here because it's a small current. Okay, what do we know? Well, let's calculate some currents. The total current is 0.32. Where else do we have 0.32 as our total current? Well, all the current has to also pass through R5 and R4. The current splits up for R3, R1, and R2, but we know that R4 and R5 get all of the current because, well, no option here. Every electron has to pass through 100, and on the way back, it has to pass through 270. So for the 270, also 0.032, and for the, the 100, also 0.032. Voltage is the current times the resistance, IR. So this one is 100, so 3.2 volts for this. And this one I gotta calculate, 0.032 times 270. I'm getting 8.64. So how much voltage is left over for the rest of the circuit? So I gotta figure that out. The voltage for 1 to 3 is equal to the total voltage minus the voltage of 4 minus the voltage of 5 because of that series circuit business. Let's take a look. So that is 18 minus 3.2 minus 8.64 is equal to 18 minus 3.2 minus 8.64 equals, I'm getting 6.16 volts. That's how much volts for the rest of the circuit. Well, wait a second. Only one resistor on this path, so that means R3 gets all that remainder voltage, 6.16. Now that I have that, I can solve for the current. It's like it's a weird game, like where you gotta play, you find information about this, that gives us, we can use Ohm's law again, calculate the missing value, analyze the circuit, get a new value, figure out what else is the same, that sort of game we gotta play. So we got 6.16 divided by 470, we're getting a current of 0.013. Okay, so if 0.013 amps is passing to R3, how much amps are passing through this? It's the remainder. So it's 0.032 minus 0.013. That means we're getting 19 microamps for both of these. And these two have to be the same because they're in series with each other. And we're pretty much done. We just got to calculate their voltages. Let's calculate. And we'll double check. So once we do the last two, their voltages, since they're in series with each other, should add up to 616. And if we've done that, we've done it well. So let's give it a shot. So the voltage of number 1 is 0.019 times 220. I'm getting 4.18. And even before doing the calculation, I know this one should be 1.98. Let's see if it works out. 0.019 times 130. I'm getting 2. Did I make I made a mistake somewhere? All right, 2.47. Okay, it doesn't add up. I gotta double check my numbers now. Something went awry. So let's check it again. 18 minus 3.2 minus 8.64 equals 6.16. That's right. Then I got the current from that, 6.16 divided by divided by 470, 0.013, right? Then I subtracted those two. Yes. And then I multiplied. Yes. I'm going to chalk this up to a rounding error. Had I taken more digits, I'm pretty sure we would have gotten a better answer here. Let me just double check. Let's start from the very beginning. So 18 divided by 570 equals. So what if we instead we took more decimals? So we're done for today. This is it. This is just me kind of going through the rest of the numbers, making sure I didn't mess up somewhere. If you still have questions, please send me an email. Send Ms. Bragg an email. We'll love to help you out. So I'm going to just try everything again with taking more decimals. Just because this last part, I should have gotten the same answer. So about 6.16 when I added these two together. I'm off by about 0.5, which is fairly significant when we talk about the numbers we're working with here. Okay, let me just get everything from the top. So I have 1 divided by 350 plus 1 divided by 470. Are those the right numbers? 350 was 130 plus 220. Yes, that seems fine. So divided by 470 equals, change, 1 divided by answer equals 200. That's fine. That should be okay. So 200 plus 100 is 300 plus 270 is 570. I'm happy with that. So let me just take more decimals then. So 18 divided by 570 equals, I'm going to keep more decimals here. I'm going to write it smaller. 0.03158. Okay, so we do that. So then we also get for 5 and 4, 0.03158, 0.03158. So then times 100, this is 3.158. 0.03158 times 270, that's the right number, yes. That is 8.527. Okay, so then I'm going to change these two here. So hopefully it was just a rounding error. Let's find out for sure. Okay, whatever. So we're subtracting 3.158 minus 8.527. What do we get? 18 minus 3.158 minus 8.527. I'm getting 6.315, which is a lot higher than the 6.16 we originally got. So this is looking good already. More promising. 6.315. Let's calculate that current by doing 6.315 divided by 470. We will also keep 4. I can't find decimal places, so let's have a look. So I'm getting 0.0134. One more decimal place. 4. Okay. Then, what do I do? Right. So then these two get the remainder. So 0.0315. Okay, so then to get the current at 2 or 1, that's equal to 0.03158, the total current, minus the current going through 3, minus 0.01344. What are we getting? 0.03158 minus 0.01344 equals change. Slightly different, 0.01814. 14. Let's multiply them. So hopefully, once again, this is what I didn't get last time because I'm pretty sure we had a rounding error. The voltage of number 1 plus the voltage of number 2 should be the voltage of 3 because they're parallel with each other. So if we're solving them separately and they confirm with each other, that means we've done that part well. which was what I wasn't satisfied with last time because we were off by a significant amount. Goes to show you keeping more decimals will help when we're allowed to, right? When we have to do sig figs, well, we're stuck. So this one is pretty much 3.99. 3.99 plus the other one, which is a lot lower than the last one. Last one I got like was 4.14, right? And the other one is 130 times 0.01814 equals, looks a lot better this time, 2.3536 rather. Okay, so if we add those two together, 3.99 plus 2.36, that looks way better. So I'm getting 6.35 when I add these two together versus the 6.315. That's close enough. Goes to show you, keep your decimals. Okay, have a wonderful afternoon, everybody. I'm going to post some solutions in a bit. Send us an email if you got any questions. Your electricity assessment will be posted hopefully sometime over this weekend. Okay, have a wonderful afternoon. I will see everybody maybe on Monday. All right, cheers, everybody.